I don't usually do this, but I'm going to hide back here this time because I want to be able to switch quickly from the computer to the document camera over here. I'm going to use some fairly new technology to demonstrate you some very old technology for doing mathematics. When people come to speak about mathematics, especially when the attempt is to reach a broad audience, they rarely do things about numbers. And I have always suspected that it has to do with the fact that if you ask the person in the street, what's mathematics about, they will say mathematics is about numbers. And so when we're trying to explain to people that there's a lot more going on than that, we avoid the topic. Nevertheless, today I am going to talk about numbers, and I'm going to talk about numbers in a particular way. Namely, I want to talk about the strange games that numbers play among themselves and the way that they have fascinated mathematicians for a very long time. Along the way, I want to try to show you how, by using some very concrete but very simple examples, how every time you answer a question, it tends to throw up a new question that you can then go and play with on the basis of the first one. So part of what I want to show you is exactly this process of the exploration of the games that the numbers are playing by way of asking and answering a sequence of questions. Now, since I've already told you that this talk has a historical component, there's a rule that you may already be familiar with, that any historical talk about mathematics has to start with the Greeks. But in my case, the Greeks is actually a book. It's a book by a fellow called H.D.F. Kiddo. And Kiddo wrote a book about the Greek civilization and Greek culture and the Greek achievement in general. And there's a portion of the book where he talks about the Greek fascination with numbers. Okay, and he talks a little bit about why this was, and I'll just remind you a few things. One that particularly struck early Greek thinkers was the relationship between lengths of pieces of string and the sound they made when you plucked two strings together. And in particular, that when the ratio between the lengths of the strings was a small number ratio, 2 to 1, 2 to 3, 3 to 4, then the two strings sound good when you play them at the same time. But when the ratio was of larger numbers, 6 to 7, or God help us, 11 to 12, then our ears hear that as dissonance. And so when they realized that, this was very, very surprising. Somehow our ears hear ratios, and they prefer small numbers to big numbers. And this was at the root of some of the Pythagoreans' speculations about numbers. There was this big Greek preoccupation with change versus constancy, with permanent things versus passing things. And they had this impression that numbers might be an example of the permanent things. So Kiddo runs through all that, and then we hit a passage where he says this. It happens that I myself, if I may be personal for a moment, was enabled to try to imagine the impact on their minds of elementary mathematics by an insomnia beguiling piece of mathematical research that I did myself. So in the middle of this book about the ancient Greek thought world, Kiddo sets out to tell us some games that he played on his own. There is actually a point, I'm not going to give you the whole text, but there's a point in the text where he has a little parenthesis saying, mathematically inclined readers are permitted to smile. And so here's his discovery. He starts by thinking of the product of 10 with 10. And he says, that's 100. What happens if I take one of the factors and bump it up by 1, and take the other factor and bump it down by 1? So I look at 11 times 9. That is 99, and it's off by 1 from the original product. Then he says, all right, now let's do it one more. Bump the first factor up one more step, the second factor down one more step, and now the difference between 96 and 99 is 3. Do it again. Bump the other one up 1, the other down 1. Now you get 91, and the difference between 91 and 96 is 5. And again, you do it one more time, the difference is 7. So you immediately have the reaction, who invited the odd numbers to this game? And then he says, and then I started adding up these differences, looking at the accumulated differences. And of course, the first one was 1. The difference between the 96 and the 100 is 4. The difference between 91 and the 100 is 9. The difference between 84 and the 100 is 16. So somehow the squares are crashing our party as well. Okay? Kiddo's comment was, they had never told me, and I had never suspected, that numbers play these grave and beautiful games with each other, from everlasting to everlasting, independently, apparently, of time, space, and the human mind. It was an impressive peep into a new and perfect universe. So, I thought we could start there and try to figure out whether Kiddo's pattern is real, and if so, why it happens that way. Now, of course, for a modern mathematician, you would immediately start writing symbols down and play with algebra, but instead we will do it the way the ancient Pythagoreans might have done it. We don't know this for sure, but there's a conjecture that they might have done it this way, and we will use little pebbles. So 10 by 10 is too much, so here's a 7 by 7 array of little pebbles. Right? That's what you get when you multiply 7 by 7. It's 49. And you get all those 49 pebbles laid out as a square. That's why the squares are called squares. They are squares because you can make them into shapes like that. Now let's think about what would happen if I set out to reduce one of the numbers by 1 and increase the other number by 1. Well, what I would be doing is taking this top row off so that now there's only 6 rows, and then I need to move those pebbles over here to make there be 8 columns. And lo and behold, there is 1 pebble left over. Why is there 1 pebble left over? Because by moving the row over, I have made it so that there's 1 fewer row. Right? Very well. And now we do it again. We take the top row and move it down to the other position. And now, now there are 3 pebbles left over. Why was that? Well, the original row had grown by 1, right? And now I took the original, that row out and brought it down, and now that, besides that extra 1, there's 2 that I need to lose to get back to the number of rows that I now want to have. And so now I have 3 left over. And again, if you're not convinced yet, we'll do it one more time. If I try to move 1 more row down, I will have 5 left over. Okay? And that's the pattern that Kiddo was seeing, that you get odd numbers, because after the first row, every time you do the process, you're really extinguishing, the row has gone longer by 1, and you've made the number of rows down by 1, so you're adding 2 more to the excess. And so you're always going to get odd numbers. Very well, so we know that part of the pattern. So where did the squares come from? Well, let me hide these out here and start making squares with the ones that are here. Remember, it was 1, and then it was 3 more. Well, 3 more, we can arrange around the 1 like that. And now I have 5 more. 5 more, I can arrange around the original 4 like that. If I were going to have 7 more, I would arrange it around the original 1 more time. And as you see, we're getting squares. Or maybe I should show you a picture with some colors on it so that you can see it in a more dramatic way. If you add odd numbers, you get squares. Right? If you take the blue number, that's 1. There are 3 green ones, then 5 red ones, and then 7 yellow ones. And it's clearly going to continue. At each point, you need as many as you now have minus 1, right? So when a 3 by 3 thing, you need, now it's 4 by 4. The next step requires 8, except for 1 that's going to go in the corner. You don't need to count that twice. So the next step requires, am I doing this right? No. The next step requires 4 more on top, 4 more on the bottom, and then an extra 1 in the corner. That's 9. Okay. So each step requires another odd number, and so you can make squares by piling up odd numbers. All right. So now we see why Kiddo's pattern works out. Now, of course, if we wanted to make it boring, we could turn it into algebra. Right? We could write down the fact that adding the odds makes squares, and all of you probably know that you can then write down an induction proof and prove that this is true for every n, and everybody is bored. Okay, so what if we start with a new question? What if when we put the numbers there, you're adding an odd number that happens to be a square. Like that, right? There I had my 4 by 4 square. The next number I had to add was a 9. Well, that means I'm adding a 9 to the 4 by 4 square. The 9 is a square. A 4 by 4 square is 16. That's a square. And I'm making a new square. In other words, what we've just seen is that 4 squared plus 3 squared is 5 squared. You all know that, right? I hope you all know that. That's a famous one. Now, if you think about it, that's actually pretty nice, right? Because you now can ask, well, okay, can I do this in other ways? Can I find other ways to take a square, add another square to it, and end up with a square, right? Now, all of you already thought of this one, right? We can take the original thing and scale it somehow, which amounts to changing your units. Rather than thinking of pebbles, you decompose the pebbles into 4 quark pebbles, and the 4 quark pebbles together double the size of everything, right? And so you end up with 6 squared plus 8 squared is 10 squared. So this is an important idea, actually. We'll come back to it, which is scaling the numbers can be interpreted as fractioning up your pebbles, breaking your pebbles into smaller pebbles. Okay? And so I made the picture there to point that out so we will remember it. So that basically means those are boring. We don't care about those. But something like this we do care about. Here is the next odd square, namely 25. Right? Did everybody see that? 9 squared is 3 squared. 9 is 3 squared. The next odd number squared is 5 squared. That's 25. And you apply the same principle to 25. And you see that 12 squared plus 5 squared is 13 squared. All right. Let's give the audience a chance to participate a little bit. Is this going to give me all of them? Can I find them all the possible ways to get sums of squares to work out by putting little borders on existing squares?
Well, you only get consecutive.
Good observation, right? Every time you do this, you're adding just one layer, which means that the bigger square has to be one step bigger than the smaller square. All right. Well, this is what it looks like algebraically. It just becomes much more boring. We're taking an odd number that happens to be a square. So if we rewrite that in terms of the number that's a square, that's the b that's my odd number, and I get that formula. And then if I really insist, I'll subtract and notice that they're off by 1. Now, just noticing that they're off by 1 doesn't necessarily mean that you can't, that doesn't give you all of them, because it could be that you always get off by 1. But you don't, because the example in the bottom gives you one that's not. Is that okay? So 8 squared plus 15 squared gives you 17 squared, and that's off by 2. Okay, so that shows you that it's not always going to work to do this off by 1 thing. And now here's an interesting move that I don't know if you guys realized could be done. This formula, as it stands right now, was known to Plato. So Plato mentions this somewhere. And he mentions even, he's clear on the fact that this does not give you all the answers. Okay? Plato didn't know algebra. Look at what happens if you sort of say, what if b was a fraction? Well, replace b by m over n, take a common denominator, multiply through by the denominator, and you end up with a formula like that. Now, that's what algebra is for, right? That's what couldn't be done by algebra before this. Suddenly, that formula that we deduced for whole pebbles actually yielded something far more general, right? I'll let you decide, if most of you already know probably, whether that formula at the bottom actually gives me all the solutions. It does give the one we mentioned. The 8 squared plus 15 squared comes by taking m equals 4 and n equals 1. So the formula, the example that we had is produced by that formula. Good. So now we know at least a bunch of ways to take squares and put them together to make new squares. Well, what's the next question?
Something about cubes.
No, that's too hard. I can't make pictures of cubes. So instead, here's the question I want to think about. The next question. What if it took 2 equal squares? Right? So let me take the 4 by 4 square and another 4 by 4 square. Well, one of the lessons you learn when you try to do these pebbles things is the best you can do is approximate squares. It's actually one of the features that's curious about the manuscripts that we have for Greek mathematics is that their pictures are always approximate, to the extent that straight lines often look curved. And there's something of a value in always working with approximate figures, because you always have to be detaching yourself from the figure. So there are 2 4 by 4 squares. Can I put them together to make a square? Well, if you're fast enough, you've figured out that you can't, not for those 2, right? Oops, I need to switch back. So here's an attempt to do it, and it didn't work because I didn't have enough red beads, right? But let's think about why it didn't work. So let me go back here and sort of say, okay, if I were actually going to do that, how would I try? Well, the natural thing to try is to try something like the putting of a square around the other one. And one way to do it would be to sort of do this. Sort of you make a hole in one of the squares, and you use the hole to overlap as much as you can the 2 4 by 4 squares. Okay? And now there are 4 beads left over, which was the hole that I made. If I was going to be able to fill out one big square, then I would need to have space, enough beads to fill them out. Now, in this case, there's not enough beads. There are 4 beads, so I can fill out up here, but I can't fill out the bottom 4. Okay? Or I could, well, okay, that didn't work. Let's try to do it a little bit better. Instead, let's overlap one more step. So now the 4 by 4 squares are overlapping all but one. Right? Now the problem is I can certainly fill out a square, but there's a bunch of beads left over. Okay? And so the question is, can we actually make this work? In other words, can we figure out a way to make 2 squares go into 1 square? Well, maybe it's just that I'm working with tiny amounts of beads. So here's a big one. Okay? So I've made a big overlap there between the 2 squares, and unfortunately there's too many green things. Right? That's how big the overlap is, and it doesn't work. So in order to attack this question, let's first ask the preliminary question. How would you do it if you didn't have to do it with beads? Okay? That's another question that has a long history. It actually comes, it gets discussed in a Platonic dialogue where Socrates is trying to convince his students that people never learn things, they just remember them. And Socrates calls over a slave boy, and he wants to to lead the slave boy to remember how to make a square twice as big as the square you started from. So there's the square. How do you make one twice as big? And of course, what the slave boy does is what most people would do when they first try this, is they double the side of the square. And as Socrates carefully explains to the slave boy, that does not work because you made the square 4 times as big, not twice as big. And then Socrates gently leads the slave boy. Depending on how skeptical you are about Platonic learning theory, you might say not so gently, pushes him pretty hard to say, well, what I want is half of this, right? This is 4 times the square, so I want half of this. So what I need to do is to take half of each of those squares. And that's easy, right? If you take the inside half of each of those squares, there's your doubled square. Okay, good. So notice we've learned something. First of all, there is a double square. You can actually do it, make a square that's twice as big as the other square that you had. It's not like we're trying to do with beads something that just can't be done. Second thing is that it tells us that the doubled square is in between. It's bigger than the single square. It's not as big as the 4 times square. So that overlapping idea is right. The overall length has to be bigger than the one you started with, but not as big as putting the 2 squares side by side. All right. Now what do we do? Is there any chance we can do it? So here's one to convince you that maybe we can. So I took 2 12 by 12 squares here and laid them on top of each other, overlapping 7 pebbles. Okay? And let's just figure out what's going to happen. How many pebbles are in the yellow selection? Well, 49, right? Now, how many do I need to fill in the 2 squares? Well, the little corner down here is 5 by 5. The little corner up there is also 5 by 5. I need 50. I've got 49. That's pretty convincing. Right? I'm off by 1. Oh, that's okay, that's pretty good. Maybe that's, if I keep pushing, I will finally, if by doing 25 million pebbles, it'll work.
Why don't you make the quadruple square and then try to cut off the corners?
Yeah, I would try, but the problem is I can't make diagonal lines with pebbles at all. I've tried. You can't tell whether the line is straight or not. Okay? So it's not completely inconceivable that it might be possible to put 2 squares together and get a square, because we're missing by a little bit here. Right? And, that's still small. 12 is not that many. Can we make it work? Well, I don't know. So maybe if we're a little insistent, there's the numbers, by the way, if you want to check that I didn't fool you. 17 squared is 289. 2 12 by 12 squares is 288. And indeed, we're off by 1. All right. So maybe if we're more insistent, we can do it. Well, sorry to say these words in the capital of the United States under the current presidency, but no, we can't. And here's the argument. The argument is very interesting, and this, to my mind, this is the one argument for this fact that I can envision the Greeks actually doing. So let's imagine in general that I took a square and overlapped it with a square of the same size, and I'm attempting to do it in such a way as for this square to be able to be broken into the corners and make a perfect square. Well, what would we be doing if we did that? We have taken 2 squares and made a big square, but in order to do that, we'd have taken a big square and divided it into 2 equal-sized squares, right? So that means that if I did it for the big square, I must also be able to do it for the smaller square. That's important. So if it happened that there was a big square that could be put together, two of those could be put together to make a single square, then there must also be a smaller square that can be put together to make a single square. But that's impossible, right? If you can start with a big one and make two smaller ones, you can make two smaller ones, and then smaller ones, and then smaller ones, until finally you're down to 2. Right? Pebbles don't divide forever. So if the size of the square gets smaller and smaller, finally you're down to this. And look, you cannot put two of these together and make a square. Not even if you align them that way. Okay, so we've proved that something is impossible, which is a kind of a surprising thing to do by thinking about pebbles, right? I mean, it's sort of very simple-minded proof of that something is impossible. So what have we learned? Well, it's interesting to ask ourselves what the Greek conclusion from this was. So let me summarize it this way. We've learned that we can draw a square that's twice as big as the one that we started from, but we cannot do this with squares made out of pebbles. So, one of the conclusions is that the length of that side of a double square cannot be a fraction. So let me show you how that works. If you had the length of the however many pebbles it was, and you could make a bigger square out of an n number of pebbles, then the ratio between the number of pebbles in one square and the number of pebbles in the other square would have to be equal to the square root of 2. Conversely, if the square root of 2 was equal to n over m, that would give you 2 squares of pebbles that you could put together to make a bigger square of pebbles. That means that root 2 is not a fraction. That's how we think about it. How the Greeks thought about it is much more like that first line in the slide, which is segments are not pebbles. Right? Pebbles are a concrete representation of numbers. Numbers are gotten by taking one thing and then taking another thing and making a little pile of things. That's what a number is. Segments are completely different. They're done by taking a pencil and drawing a line along a ruler. There's no things. There's no pebbles made up making up that segment. And so the Greek conclusion was that's just two different kinds of things. Numbers are the things you made out of pebbles, and lengths are lengths. Okay, so that's one of the things we've learned, that lengths are not numbers. Tell that to your high school students. But what about the near miss? So what does this tell us about the near miss? Now that we know that you can't do it, well, what does it tell us? Well, look, the near miss happened because when I tried to break 7 into two 5x5s, I was off by 1. So in other words, I get an off by 1 between 17 and 12 because I have an off by 1 between 7 and 5. Right? So one near miss deserves another. Because 17 squared is equal to 2 times 12 squared plus 1, or maybe it's the other way around. The big numbers do that because the smaller numbers do that as well, except that now it's minus 1. And you keep going, right? Right? Well, that was exactly how we proved that you can't make it work for 2 by 2 for doubling squares. So what happens with near misses? If you keep pushing them down, you should also get down to just 1. And lo and behold, you do, right? So here are 2 pebbles, and we try to put them together to make 1 square. There it is, and we have 1 left over. So there's no problem this time, right? You can actually do it with 2 pebbles, therefore there's no contradiction. Okay? And for people who have studied some number theory, you know But if you haven't studied some number theory, you can figure out that if I could start from 12 and 17 and push down, I must be able to take 12 and 17 and push up. So the next step up, you can even figure out what the relationship is, right? The new big number that has to show up, the smaller number that has to show up is the sum of the two numbers that you started from. So 17 and 12 are going to produce an identity with 29. And then the difference between the smaller number and the bigger number is equal to the smaller number in the original equation. So 29 plus 12 is 41. So that's how you get the 41 and the 29. So homework assignment, figure out how to do the next one. You know how to do the next one. You add the two, you get, what do you get? 80. And then the difference has to be 29, so the other one should be 109. And then that's well beyond what I can do in my head. But what? 70 and 99. Yeah, okay. I hope it's right. We'll see. All right. So one of the points to make is the way that each of these answers led to a new question, right? So we figured out how to put together squares of different sizes and made a square of a larger size, at least when we were lucky. We tried then to put together squares of the same size. We couldn't figure out how to do it, but we discovered how to do it with line segments. And then we proved we couldn't do it with pebbles, but we also discovered that you can almost do it with pebbles. And by using the same argument that proved you cannot do exactly, you also proved that you can make as many near misses as you feel like, right? If I had wanted to be really impressive, I would have done a 10-digit near miss, right? Just keep cranking this machine, produce this big number, and then you're off by one in a 10-digit number, which is so small that nobody would be able to even just see the missing dot. All right, so nice. So what's the next question? Where do we go from here? Now, we don't have too much time to play games, but let's sort of mention some things that one could do. Well, one question is, what else can we do by putting together two squares? So one example is, can we make prime numbers by putting together two squares? The answer is yes, you can. By the way, in Pebble Land, how do you tell a prime number? You can't make a rectangle except in the stupid way, right? You try to make a rectangle out of a prime number, it only comes out a straight line, right? So you're looking for two squares so that when you mash them together, the only rectangle you can make is a straight line out. And yes, it can be done, right? 2 squared plus 3 squared makes 13. And natural question to ask, which prime numbers can you get? 4n plus 1. How do you know? It's really easy to prove that you can't get the other ones. Right? You can't get the other ones because you just look at remainders when you divide by 4 and you show that the other ones are impossible. But to show that you actually can get all the 4n plus 1 primes, you need to do something magical. Okay? I'm not going to show you. Fermat had a proof that was basically pebbles, sort of basically it moved by going downwards, but it was very, very complicated. A modern proof would involve looking at how primes factor when you make the world more rich than just the ordinary numbers. What about 3 squares or 4 squares? I've written the answer for 4 squares. You can make anything with 4 squares. No, actually, you have to be careful. If you allow up to 4 squares, you can make anything. Okay? But that's sort of an example of how to push this question a little bit further. Sort of what can you do if you allow that sort of thing? I should point out, by the way, that the Greeks pretty much knew this as well, though they don't quite say it. It's sort of in the air in some of the Greek work. They certainly know about square numbers and this idea of laying them out, but there's some indication that they do know that, but not anything explicit. How about other shapes? So here's a triangle. So how do you make triangles? We made squares by adding odd numbers. Does anybody see how to make triangles? You just add numbers, right? You take 1. Nicomachus calls this a potential triangle. Then you take 2. Then you take 3. And then you take 4. I guess the one I had was 15, which is the one you got when you do 5 by 5. All right? So what can you do with triangles?
Put 2 triangles together, make a bigger triangle.
Can you?
I don't know.
Well, one thing that you can do is kind of cool. Let me take the triangle with 10 things and try to put 2 triangles together in a different way. I'm going to organize my triangle like this. What happens if I take another triangle with 10 things and put next to this one? You do not get a square. You do not. You get a rectangle. Right? So, except it's hard to see, so let's separate them a little bit. Now I completely messed it up.
And 1 more pebble, please.
Yeah, we need more pebbles. Okay, there. So, if you separate them, what I need is a pen to put between the 2 triangles. There we go. Right? If you take the 10 that make a triangle of base 4 next to another 10 that makes a triangle of base 4, it makes a 4 by 5 rectangle, not a square. You can make squares as well, but you need triangles of different sizes. Okay, so that's already an example of something cool that you can do. Here's another question. Can you ever have a square that's also a triangle? So let's see. 15 is a triangle. How do you make the next triangle? Add 6 beads at the bottom. That makes how much? 21, not a square. Add 7 beads at the bottom. 28, not a square. Add 8 beads at the bottom. 36. All right. It is possible for a square to be a triangle. You can't square the circle, but you can triangularize the square. Okay. Those are other questions that you can play with. What numbers do you get if you add up to 3 triangles? Right? Yeah, Dan knows the answer. All the numbers.
That wasn't a no, that was a guess.
Yeah, but that is the right answer. The amazing theorem here, and this one is one that was only proved in the 19th century, is that you can make any number whatsoever by taking up to 3 triangles, up to 4 squares, up to 5 pentagons, up to 6 hexagons, up to 7 heptagons, and so on. And that's sort of kooky. What the heck? Why is that true? I'll let you think about that. The problem of numbers that are both squares and triangles is related in a very weird way to the near misses. Okay? And I'll show you how. It's basically this. Let me first tell you, and then I'll show you the pictures. If you take a square that's also a triangle, first you can take 8 copies of that square. 4 copies go together to make a bigger square, twice as large on the side, and 4 other copies make another square, so you get a double square. But if you take 8 triangles, you can almost put them together to make a square. So here's the picture. Here are 8 squares. They're all 6 by 6 squares, because 36 is our example of a square triangle. And here it is put together as a big square. Now what's going on? In each one of these, I've put a 36 as a triangle, next to another 36 as a triangle. That makes an 8 by 9 rectangle. And laying together 4 8x9 rectangles, you almost make a 17 by 17 square. You're missing the single pebble right in the middle. Right? And so there it is. Somehow, every time you have a square that's also a triangle, you also have a near miss. Therefore, there are infinitely many squares that are also triangles, right? Because we know how to take a near miss and make another near miss. Actually, you have to be careful. This is a near miss with a +1 and not a near miss with a -1. But if you have a near miss with a +1, and you have to take 2 steps to make the next near miss with a +1, if you take 1/8 of the right piece of it, you will get a square triangle. Right? So there's as many square triangles as I might like, because there's as many near misses as I might like. All right, I will stop there. Oops, this thing goes back to the beginning. But let me point out that there's a world to play with here. There's pentagons and hexagons, so I'll tell you one more interesting theorem about these guys. This one the Greeks did know about. It goes like this. When you want to make triangles, you add together numbers that are in steps of 1. You add 1 plus 2 plus 3 plus 4 plus 5 to make triangles. When you want to make squares, you add together numbers that are in steps of 2. You take 1 plus 3 plus 5 plus 7. If you want to make pentagons, you start with 1 and you add together numbers that are in steps of 3. You get 1 plus 4 plus 7. Those make the pentagons. Okay? Nicomache's old theological arithmetic explains all this and tries to make a lot of mysticism out of it. It's amazing. You can just keep increasing by 1 the number of the step. You can lay things out. And of course you can do cubes and 4th powers and things like that. The problem with cubes and 4th powers is 2 problems. First is it's too hard, right? You can't even draw the pictures anymore. Cubes you can sort of draw. You could take sugar cubes and try to put 2 cubes made of sugar cubes together into one bigger sugar cube. Anybody know if you can do that? Take a cube made of sugar cube blocks, another cube made of sugar cube blocks, put them together and make a big cube. No, that's a little piece of Fermat's last theorem, right? That's asking for the sum of 2 cubes to be a cube. You can't do it. You can do it if you have more cubes, though. Right? I think the standard example is you can take 2 cubes made of sugar cubes and then rearrange them into 2 other cubes made of sugar cubes. Right? That's Ramanujan's taxicab thing, right? The numbers that are equal to the sum of 2 cubes in 2 different ways, except his number is not a cube that's equal to the sum of 2 cubes, but you've got to at least do that. Okay. And so let me just end with this idea that there are immensely many of these games that numbers play with each other, and you can always find one more mystery to play with. Some of them will be stuff that people have known forever and ever. Some of them will be easy. Some of them will be tremendously hard. And what I want just to give you an idea is how much fun it can be to try to find out. So thank you.